All right, so good afternoon, everyone. Today we're going to talk about the recent HotOS paper in reference to RPC. It's time to add distributed memory. Unfortunately, the original presenter didn't reply to me, and it looks like he's not here. So I will try to cover to the best of my ability. I managed to prepare some slides, but it's not a comprehensive set of slides by any means. So yeah, let's talk about RPCs. First of all, what is an RPC, right? So RPC stands for Remote Procedure Call, and really it's this common, very popular communication primitive where one program, we can call it the caller, invokes some function, some method procedure on a remote machine that we can call an executor or worker, right? So it's a pretty simple idea, because the executor is remote from the caller, we have this situation that it's a distributed system in a sense, and the caller and executor, they don't share any memory, right? So they run in completely different memory address spaces, they're completely different machines. And because of that, the RPC framework is built on this idea, on this notion that all of the values, all of the data that has to move between the caller and the executor, it is passed by value, right? So it is actually copied from the caller to the executor, and the return values are copied back. So in my little example here, we may have two available functions at the executor side, f and g. They take some parameters, they return some values, right? And the caller, in this case, calls the function f, and it actually passes the value, some integer 42, and then it will get the return value, again, passed to it, copied to it, when the function is done executing on the executor side. And this works really well, especially when we have small values, right? When the parameters and the return values are very small, then this approach works decently well, it's simple, right? So we also never have to worry about things like references, right? And losing the reference and things like that. Everything is copied by value, right? Or like you don't worry about things being modified in place, like in memory, and then the object changes and whatnot. But we do have some problems with this pass by value kind of approach. One problem is we may have parameters or return values that are very large, right? So if they are large, then we're just not potentially using the network very efficiently, right? Especially if we need to reuse some of these values, right? Or propagate them through a series of RPC steps, right? And in that case, like every time you invoke a new RPC, even though you have to reuse, if you reuse the value, but you have to recopy and retransmit it on a network to another RPC call, and so on and so forth. So we can lose quite a lot of efficiency if we have this like steps of RPC calls that tend to reuse the values or chain together. Yeah, these inefficiencies, and this is kind of because of these inefficiencies, we in the engineering community, we tend to come up with these ad hoc solutions that are very application specific, right? So maybe if we need to pass these large values or chain them in any way, then we can create a separate like shared key value storage somewhere that both the caller and all the workers have access to. And then when we call the RPC, we pass the key to some object that's stored in this shared key value store, right? So we add this shared memory at the application level, right? And obviously, when the values are small, that's quite inefficient because we have to like keep contacts in this shared store. When the value is so large or reused a lot, then this leads to improved efficiency, right? But at the expense of having these extra steps and at the expense of having to implement all of this ad hoc at the application level. So obviously, because this is done at the application level, we tend to run into quite a few problems. Some problems are so like the semantic issues. It's not very inherent to the application level implementation, but it does show up, right? So semantically, in RPC, everything is copied, everything is passed by value. So now we have to answer questions like, if we have this shared memory, can we update the objects in place, right? So can the objects become mutable? Because that doesn't exist in the copy in a pass by value kind of environment, right? You get the new copy of an object all the time. You can do whatever you want with it locally. It doesn't impact any other parts of your system, right? Any other functions or whatnot. So the mutability of object is semantically different in the shared memory environment versus the RPC environment. Another issue that we have to address with this application level solutions in particular, right, is when do we clean up the shared objects, right? Like, how do you know that the shared object is no longer needed? So now we have to essentially code the application to do this very fine-grained memory management, like the cleanup, right? So obviously this can lead to things like memory leaks and the shared storage and issues like that. Because again, we're dealing with this distributed system, right? So we may run into problems on how to decide where and when to move the data in the shared storage, right? If the shared storage itself is distributed and you have multiple workers, then issues of locality, of data locality, right? Collocation of the data and the processing start to come up. And again, in the application level solution, these issues have to be dealt with somehow at the application. So, we will complicate the code of the system of the application relying on RPC a lot by doing this. And there is no guarantee that some of these problems can even be solved in an efficient way, to be honest. So yeah, another issue is how to ensure that the workers, executors, are not overwhelmed with this reference pass, right? So the paper kind of mentions this a little bit, or a lot of it, but if we have copy by value, right, pass by value, if we copy the value, then the workers, when they start executing the RPC, they already have memory allocated for all of the parameters, right? So it's a little bit easier to anticipate the memory consumption because you already at least you already have all the input data in memory at the time you start executing, and that's not the case here. So it becomes more difficult to predict if you have enough memory to run this function, or even if you have enough memory to fetch all the data that's needed for this function, right? So that means that it's easier to overwhelm the workers that have access to this shared memory and pull these large amounts of data from it. So the vision of this paper, right, the proposed solution is to have this better system that puts this shared memory approach directly into the RPC framework, right? So that we don't have to deal with all of these issues at the application level. That's kind of the schematic figure that they present on the left. That's more traditional RPC approach where the client, the caller, sends this RPC calls to the servers, but it goes through the load balancer, right? So it's a little bit more complicated than my super naive example. We do have a load balancer that will pick the best, server or round robin or whatever, right? But the basics are the same, right? The data is being copied from the client to the server that executes the call. So what this vision says, we already have this load balancer. So why not we change it into something a little bit more complicated, that will include the scheduler and the memory management aspect for this entire shared memory system, right? And just like before, just like at the application level, we're going to build some kind of shared, distributed, in-memory key value store to act as this distributed object store, to act as that shared address space, so to speak, for this RPC framework. So yeah, quite a lot of paper goes into details and some details, right? Some like ideas on what this may look like. They do provide an API, like a suggested API for this RPC framework. The key things here are that the parameters can be passed by value or by reference, right? So we can pass stuff by reference in the when we want to invoke the call, and the returns are passed as futures, which are references that will point to the data once the call itself, once the function is finished on the remote side. So, and since we're passing all of this, okay, I think I'll get to that later. So yeah, like they provide this sample API, right, where you can, so reference is just the reference that to a data stored in this underlying distributed storage. Shared reference is taking this reference and making it passable in an RPC. So that's, I guess, really like puts it into the storage. The remote call, that's the implication of this function f on the remote machine. It passes the parameters by reference, and it will receive the reference to the return value. So yeah, I think this one, what they refer is kind of implicit. So you can pass the value and the system will convert it to reference. And this is the shared reference that already exists in the system. So you can pass the actual shared reference, or have the system implicitly convert it and manage the lifespan of this reference for you. Get reference. So that's the referencing of this reference R. So that's pretty much retrieving the data from this shared distributed store. And delete, that's the call used to manage control the memory, right? Control the address space in this distributed storage and clean up the data. So what they say that it's like delete, for example, is not even exposed to the application because this is going to be handled by the framework, by the RPC framework. So using these references and futures allows the system to keep track of all objects still in use, right? And that's because all of this references and how they passed is going to be controlled by this load balancer that turned into schedule and memory management, right? So this guy knows of all the kind of active references, right? So this allows us to build this automatic memory management system, kind of like a garbage collected language, right? Where this memory management subsystem component will keep track of how many alive references to a particular object still exist, and collect them when there are no references still needed. So another thing about this memory management approach that they forgot to mention and they kind of build upon is that the memory itself is it's immutable, right? So once you write something to the storage, you cannot change the object. So it kind of preserves the semantic of the RPC calls. So if you produce something new, you have to create a new object for that and a new reference as a result. And yeah, so again, having this scheduler and memory manager co-located allows for this, allows for some neat optimizations that deal with the locality awareness, right? Because now you can, now you have this one component that knows of all the workers that can execute the different functions and all the distributed storage subsystem, right? All the references that exist and where they exist, like physically on which machine, on which replica of this distributed key value store, for example. So then they can schedule things more efficiently. They can, if some references for like a big chunk of data, the scheduler can schedule this data to be processed on the machine that already has the copy of this data, right? So it doesn't have to be moved again. So yeah, I guess putting everything into the framework allows to get down to this kind of low-level optimizations and allows to unload the application developers from the burden of like managing this shared memory and things like that. So finally, I think I'll finish with the fact that the paper does mention that what they propose is not like totally new, and that a lot of the features that they have described that will enable this shared memory RPCs, they do exist in some of the systems, but these systems tend to be more domain specific, right? And part of the vision is to try to make it more general, right? So instead of having a domain-specific system that kind of has these features, we can build a general RPC framework that actually allows to compose multiple systems and subsystems with the same communication style. And there are quite a few challenges that obviously exist, and the paper briefly goes over them in a paper's discussion section. If you start to compose in different applications with this framework, and these different applications, for example, have different ways to deal with the faults, right? Then you need to have your framework kind of being able to handle them and handle these different fault handling mechanisms and glue the applications together somehow, despite different fault assumptions and things like that. So yeah, I think that's all I have. I apologize for like a very mumbly presentation. I didn't have a lot of time to prepare for that properly. So, thank you.